Meziani, who is going to tell us about the origin of the Proton mass.
All right, first, thank you for the invitation to me, and thanks to the organizers for the invitation. I'm actually very excited and happy to hear the discussion among the theorists. And so what I want to do is kind of try to give you a sense of, at least from an experimental point of view, what was the interest for me and some collaborators to actually do measurements to connect somehow to the theory, answer some interesting questions. So the talk is based on something that we wrote with my postdoc, Sylvester Houston. This is not, it's reflecting here, but the stick is good. And the outline is, I want to look at the science that's enabled by the heavy quarkonia in the threshold region specifically. And in that case, I will discuss the elastic threshold production of charm, JSI, on the nucleon at JLab. And I will actually continue with the elastic threshold production of beauty on the nucleon at an EIC. It's actually quite complementary. So in terms of the EIC science, assessment by the NAS, the first finding here is articulated through these three science questions. And the first one is, how does the mass of the nucleon arises? So we think that, you know, this is kind of an important subject, and having the community looking at it in details will benefit us, not only that, you know, it's interesting science, but also in terms of communicating with the other disciplines. Now, if you look into the subject of production of quarkonia threshold, in fact, really before the discussion about the mass or the origin of the mass, there was interest a long time ago. Of course, this was one question that was discussed, but at least theoretically already in the 90s, early 90s, but people were also interested, what is the size of the interaction between quarkonium and proton, and this is talking about color van der Waals forces, so between two color neutral objects. That by itself was an interesting subject. Now, more recently, of course, the question is whether heavy quark enable actually the existence of pentaquarks, and if so, we need to kind of look at this problem a little more you know, in terms of measurements and theoretical possibilities. And last but not least is, are the bound states of quarkonia in nuclei possible? This is also a very interesting subject and needs to be taken seriously, you know, whether it's at an EIC or any other facility. So the threshold electro and photoproduction of quarkonium can probe, at least this is something that was stated, and I will come to it later. The electron and photoproduction of quarkonium can probe the mass distribution of the proton and, of course, of nuclei. Oops. So now the question, of course, all of you know this is nothing new, that QCD takes us a long stride towards the Einstein-Wheeler ideal of mass without mass, where the discussion, whether it's the long-range plan or any community that's dealing with QCD, we know that 1% of the proton mass, and we heard more specific numbers, but you know, the folklore was that 1% is, meaning current quark masses, is taken by the quarks for the proton mass, and the rest is coming from the dynamics of, you know, gluons, and that becomes an important thing. I don't see this clearly, but I actually had a video of Lenny Susskind giving a public lecture when the Higgs was discovered, and it's fascinating because he took two examples when he was trying to explain of how we can acquire mass, of course, without having the Higgs mechanism going on. And the two examples he gave in nature was one, the proton, and the other one, black holes. Of course, when you are discussing black holes, you can also see how people discuss black holes in terms of basically masses, but masses through energy. And I find it actually quite interesting that he used those two examples in the same speech. And we know very well this figure. This is another way of looking at the nucleon in terms of 3 quarks and seeing that, of course, in the low energy momentum regime here of the quarks, you are picking up mass in such a way that it's all the dynamics. Now, this discussion I remember clearly. I'm sure that Abe here remembers that too, where the theorists started to argue about whether it was 1% taken by quarks or 10%. Somebody says, who got this number from what? And that really triggered the discussion about what lattice can do actually to help us understand this. But I just want to remind you, this was already quite early. Let's see, I don't see the date here. But this was the first paper early on to tell you that, look, you know, great, wonderful success. Here are the masses calculated. Of course, there are these inputs, which is this point, that point, and this point. But typically, lattice has been doing even more progress in looking at mass differences between protons and neutrons and so on. So this is great. However, we really need to move further. And the reason why we discuss moving further, again, is it's important to actually communicate with the rest and talk about what are the constituents. You cannot discuss the constituents of a system and then when it comes to the mass, you start to wave your hands and you say, oh, it's complicated. So trying to find a path, not perfect, I can see the deep discussions that you guys were having, but to say what is the role of quarks and gluons, it might not be unique, but I think it's important to have that discussion. So the thing that I like very much from an experimentalist point of view is that when I look at any decomposition or any sum like that, my personal interest was, is there any measurement that allows me actually to then look at these physical quantities and see whether I can understand them from a measurement point of view, and if there are predictions, whether it's from lattice or from models, whether we can directly check them. So if, at least for people like me, I go to textbook, and if you go here, you learn about scale invariance and how classical theory will give you 0 when you are looking at the trace of the energy momentum tensor. However, fluctuations for quantum field theory are going to tell you that, guess what, when you have the trace, you have 2 pieces. So typically we write 2 pieces. I have to be very careful. Actually here it should extend, and I'll come to it in a second, UDS, but then you have, of course, John, top, bottom, also that you have to include. And the interesting part is that this part, of course, from a measurement point of view, you go to the pi and sigma term. People have been working on that for a long time through measurements. Lattice calculations have been going at it right away. But what I found amazing is that in some sense, there is no direct lattice calculation of this piece, even though you saw the other lattice calculations, and no measurements per se at this stage. So it made it interesting just to say, you know, it would be nice to look at these 2 terms from a measurement point of view. Of course, when you are doing lattice, you are doing model, taking the chiral limit is a very important and nice thing to check yourself and understand things better. And in the chiral limit, as we were discussing yesterday, of course, the proton has a finite number, so that's given by that term. But if you did the same for the pion, this term actually gives you 0. You take the chiral limit in the case of the pion, and you get 0 for the contribution of the gluons. That is just the masses that are giving you the mass of the pion, and that goes to 0 also. So in the chiral limit, the pion, for whatever reason, cancellations and so on, this piece, that's there. Gluons are there in the pion, will give 0. All right, now I just want to say that, of course, I don't want to give you that, again, the same problem that we have 30 decompositions and, you know, what do I learn? But from observing discussions between people, in theory, at least there is not much of the debate on this trace decomposition, which was the one that has just 2 terms, right? The gluonic term and then the one. Usually people are kind of okay there. the discussion starts to heat up when we go here, or as you just heard Lorsi explaining, this other way of looking at the decomposition. Yes, please.
So with regard to the first term,
Yes.
I mean, I remember a conversation with Mike Kreutz, his argument was he didn't understand the first term because he could define it on the lattice. It's IDUV. So how do you think about that on the lattice?
I mean, yeah.
But maybe Yoshitaka has
It's a continuum, it's very different.
So I can
Just because it's just too difficult.
But if you think about, you know, think about any quantum field theory as having some kind of regulator, and lattice that's perfectly good regulator. Then,
Well,
so
then,
how do you
yeah,
think about
I think there's particular difficulty about this. About the trace of
I mean, you cannot think about a quantum field theory without a regulator.
I think what has to be true is to calculate the expectation value of the operator and a proton state and subtract off the vacuum, and the solutions just have to go away.
But these are, yeah, I agree with you, but then these are quadratic divergences.
They're hard to make them go away, but they do go away.
Okay, I agree.
All right. So this is wonderful. No problem. Actually, this is the reason. So the way I learned about this is already in 2012. I wasn't looking at the origin of mass. I was very interested since the 90s about what Stan Brodsky and collaborators, the Tiramo and Schmidt, trying to look at color van der Waals forces. And at that time, I started to look at these papers, very exciting. But more recently, in fact, the proposal I'm going to show you, at least the projections, were in 2012. At that time, we used all the arguments I'm using here to actually try to do the measurement of J-psi at threshold. And that was really, for me at least, I had the support of Dima Karziev, because even at the PACJ lab, I had sentences from him that were signed and approved by him telling me that this is very important to measure. And the key there is that you can see that if I write it here, I have all the quarks together. Of course, I was looking at Cédric Lorsi. He has the complete references. I'm starting in, somewhere in 1978, but there were references, of course, before. But the point is here again, this term of the trace anomaly, the contribution of the light quark, and then of the heavy quark. And the trick in his presentations that he gave, he actually says that at small momentum transfer, the heavy quark decouples. So this becomes then, these contributions become something that's again proportional plus whatever. Of course, the whatever, it would be good to test what that is if you are doing lattice QCD also. Because in lattice, you could calculate these matrix elements, and people have done it for the J-psi, and you could actually check whether this type of relation or whether there are extra terms here that you are missing. But the bottom line is that he replaces this beta with the beta tilde, and you have then a sum only on the light flavors, which then tells you about the pi and sigma term, which you measure, and this you will try to access through, again, the subtraction operation. All right, I don't spend time for the rest frame decomposition. You know what it is, and Cédric Lorsi discussed when he included pressure effect. The one thing I must say as an experimentalist, for me it was actually quite important to realize that, look, yes, the mass of the proton is something that, as I was hearing in the discussion, if the thing moves, it's not an invariant. The only thing when we speak about mass, if I open the data particle book, I know what mass they are giving me. It's in the rest frame, so I have no problem with that. So if everybody agrees that the rest frame is okay, and that we can interpret any measurements in the rest frame, then it's okay. But if there are technical difficulties, that's a different story. But rest frame doesn't bother me from that perspective. But same here, the trace anomaly and the way the decomposition was made, it told me that, okay, some people like this, don't like this, but that's fine. I need to find a measurement that allows me that. So there were two workshops, one in 2016 at Temple, one at the ECT as a follow-up, and we really wanted to look with actually John Way, Chu, and Mark Vanderhagen and Barbara Pasquini, to look at few things: lattice QCD, mass decomposition role of the constituents, and also the approximated analytical or model approach. In other words, you have approximation that you can control, and that's quite important. But questions like what can lattice QCD do to explore the role of individual constituent making up the proton mass, such as the role of quark mass, strange and heavy quark masses. These are the type of problems we wanted to look at, and so on. And you know, the websites are accessible, talks are accessible on these. So let's get to the experimental part. So naively, what we wanted to do is, of course, to explore this process. And to explore this process, of course, I have a diagram here where it's a blob. I don't know what's going on here. And a diagram here where, you know, common wisdom, if you were at high energy doing imaging and so on, nobody is going to argue with you. You put your two gluons there to conserve your color, and that type of exchange is kind of okay in the way the theorists look at it. Once you start to get a threshold, I don't know what this means, but you know, it means a blob. However, you know that you have to exchange something that's scalar between the two. So the idea is that at JLab, we can measure the threshold region in photo and electron production. And in fact, it's being done in 4 holes, and I will show a few things there. We can have also fully exclusive, if we want, at JLab. And the detection of the lepton pair, in case of the photo and electron production, can be detected in coincidence also with the proton. At an EIC, we can detect the scattered lepton, the upsilon decay pair, and I'll tell you why we choose the upsilon at some point. And of course, detecting protons is challenging, so you need to talk with the experts who have been looking at forward detection, how they can pick up proton. At HERA, for example, they didn't, because it was just saying that you don't have activity going on in the detector, but they did it without the detection of proton. What is there in terms of data? So you can see that including LHCb now, things are working quite well at high W. So if you are doing imaging, or if you want to look at this region for the J side, it's actually quite good. The problem is that when you look actually at the threshold region, you don't see much. And you don't need to think about it with the mass of the proton problem. You just think about it from the point of view of, you know, 40 years later, we still don't have data because all this data thresholds were coming from Slide and Cornell. At the time when they were just in fixed targets, and they wanted to kind of confirm that the J psi was there because it was discovered in plus and minus at that. If you look at the upsilon, I like this picture very much because it tells me that if you want to really, like, you know, bring the EIC and also do some measurements that they couldn't do at HERA, the upsilon is a very nice candidate. There aren't much data here. So that's what we'll be discussing. So I'm not going to discuss the tomography, of course, but I just would like to make one comment. I think it's as important to do a very good job and to look at imaging. In fact, in that paper, we looked at profiles doing the upsilon as the J psi. If we talk about interpretation and universality, it would be nice to say that the gluon density we get from this imaging is the same whether we use the J psi or the upsilon. And of course, ultimately, you also have a second order the DBCS, where after you have all the data and you do the evolution, you can also compare. So this is important. Now, in whole JLab, I'm showing the 4 holes because actually there are plans in the 4 holes to look at the J psi. So this is hole D. I will show you these preliminary measurements that Rolf actually already showed. Then you have hole B. They are taking right now data, and there's improved proposals. So they have the J psis that are coming in. I don't know actually what's the status, but I can show projection. Then there is in hole C. In hole C, we have very soon coming, just at the end of January, a search for the pentaquark experiment. And this is done with 2 spectrometers where you are basically assuming elastic scattering using a Bremsstrahlung photon beam and you are detecting the pair E plus E minus using spectrometer with high resolution. Last but not least is solid that Jianping yesterday told us about in terms of measurements. And this was an approved experiment that was actually approved in 2012. And you know, we discussed anomaly, but people, you know, PAC sometimes, of course, you have to be insistent, and they came around, but the proposal was approved with an A minus. So our hope is maybe to come back and to convince them that it should be an A type of proposal. All right, so the resonant JSI production through the PCDK. I will discuss first the pentaquark quickly. So if this LHCb pentaquark is going to is a real resonance, then it should be we should be able to produce it in the S channel directly in photoproduction. And these are the two diagrams. You can forget the U channels. This is the dominant channel. And if you look at the what you can do in hole C, and I'm just using two spectrometers to detect the JSI, it's a pair. So this is a high luminosity but very small solid angle because you don't have this 4 pi type detectors, but you can put a radiator and you have a huge amount of photons. So it takes 1 day to do a good measurement of the T channel, meaning this exchange, that scalar type process, which is usually how we look at the JSI production. However, if you have a resonance which you would produce through a pentaquark, charmed pentaquark, then what we did is we optimized the kinematics so that the phase space, if you are here, you are dominated. So this is T versus the energy of the photons. If you are doing T channel measurement, it doesn't take much because, as you can see, the rate is very high. So we set up the spectrometer in such a way that we look into this region where we are suppressing the T channel production, so that we can enhance if it's there and have sensitivity to actually the pentaquark production. The setup, two spectrometers, it's 10.6, 10.7 GeV, a 9% copper radiator, 15 centimeter liquid hydrogen target. So you have a radiator, when you add the target together, is 10% radiation length. These are the two spectrometers in hole C, standard detectors. It gives you here the type of angles and energies, but typically we will sit there and measure for 9 days the pentaquark type configuration, and 2 days, what I call background here, is really the T channel production, is what we usually want to measure. Look what happens. For that type of kinematics, the T channel, which is this red curve that you see down here, is suppressed. That's because of the choice of two spectrometers. And then if there is a pentaquark with a 5% coupling, so this is in one of the models that was in the literature, which is listed here, you can actually see a nice peak. So now you could say, well, but when do you stop? What does it mean that you see something? And can you set limits? In that case, quantitatively, if you say that the discovery at the 5 sigma level is what you would require, okay, then for this experiment, typically what happens is that depending on the coupling, which is listed here, this gives me the sensitivity in number of sigmas. So I put my line at 5, and you can see the projected sensitivity. So we are planning to have 1.3% coupling at a 5 sigma level, and the spectrum would look something like this. So here it's a 1.3% coupling. We are sitting there, and this is for the full experiment, which means this is the type of sensitivity we can have. You see here the T channel is taking a little over. This is kind of a peak, but at least we can quantify it. All right, many models. I didn't want to say that your work is not important. I put it here, but typically what has happened, typically you had modeled by Stan and Lager and Shudikov, Frankfurt and Strickman, 2 gluons, and they tried to fit whatever exists. There weren't data, really that much data in the threshold region. And it was always discussed with 2 gluons, whether you talk about 2 hard gluons or soft gluons. You know, that's to your interpretation, but at least they give you some analytical expression with which you will use as an experimentalist to make projections for your measurements because you can't go to the PAC without a number of days. So the drop here is quite high. The work of Hatta is interesting because I was telling him yesterday that in 2012, when I was talking to him, the reason I want to talk to him also is I thought, oh, this is a non-contributing region. Is there a way that in the CFT could do something? Because he can't really do it the same way. So I'm extremely happy to see his work. Now, I go back to the way the proposal was defended at JLab, and this was from the cross-section, how you connect to the trace anomaly at some level. So the discussion goes like this. Of course, we are assuming VDM first for the mechanism. So to get to the amplitude of J psi, proton goes to J psi proton. Since I'm measuring gamma, proton goes to J psi proton, I need to use a model. So you might not like it, you throw all of this away and say, you know, this makes no sense what you're doing. This was done by Dima. You can see the references here. And the bottom line is, once you do that, then you are connecting this scattering amplitude of J psi nucleon squared through the differential cross-section at t equals 0. So if you do that in the region here, you can see that it's really the real part that's dominating the cross-section in the threshold region. And the rest is part of the imaginary amplitude. That one, of course, you can fix it through all the measurements at high energy. What is interesting is that if you have good measurement at high energy, you could also use dispersion relations to actually constrain also the threshold region so that you constrain the contribution of the real part. So the bottom line is that if you can go, of course, to the region of threshold, you can put constraint on this amplitude, which you can connect also to that matrix elements that we were discussing, the gluon square. In fact, he has a very nice lecture where he can go also to, you know, you cannot resum all these gluons. So you have an infinite number of gluons. You cannot resum those. People are looking into that, but with Dima's model, you know, the next thing is you deal with pions, and you have a 2-pion exchange, which would get you there, because with pions we know what the coupling constants are. All right. Of course, again, you know, there are limitations for now. Binding. So in a recent paper by Gridyuk and van der Hagen, what they did is they refitted. This is d sigma over dt at 0. It's similar to what Dima has done in his trying to understand that region and get the matrix element. And in this paper, what they did is they used the dispersion relation, and they could actually get this piece to connect it to the binding energy between the nucleon and the J psi. And in their conclusion is that they can actually get a scattering length. From the scattering length, they can get a binding, but the binding, they use nuclear matter, and you see that it's quite small. So you can argue that if you are interested in the binding of the J psi nuclei, it might be quite tough, but it's something also that would be interesting to look at. But more important, the reason I wanted to show this is not necessarily the fits and the fact that there is little data, because this is cross-section, is in their second part of the paper, they take advantage of interfering the J psi production with the Bethe-Heitler production. And in that case, they claim that there is an asymmetry that shows up that actually connects you to the real part of that amplitude that we were talking about. And that connection is obtained by an asymmetry that you measure. So this is a forward-backward asymmetry in the center of mass of the invariant pair. And in the lab, it means basically that if you have a symmetric configuration, you just switch the positron and the electron, and you measure the rates, and you see that there is a difference in rates. So this is theta center pass minus phi. These different curves that you are seeing here corresponds. You see, I have the t equals 0, t psi, p 22 and 45. This is what they used here. So you can see that you have actually quite good sensitivity to that piece that you need to extract.
Just positron electrons going in opposite direction.
That's in the center of mass. Of course, it's either the positron goes forward or the electron goes forward. There is an asymmetry. Yes. In the lab, then it's like, if you look at the symmetric situation, you go pi. So you flip the two, the detection of the positron on one side versus the electron
So
on the other.
left-right asymmetry.
Yes, in the lab. All right, so with this, I think it's important to realize one thing is that to do this asymmetry, this is an asymmetry, which means that to get high precision, it's quite hard. And you do it in a region where you're not sitting on the top of the JSI. You have to move it away a little bit so that you interfere with the Heitler, so that the cross sections are of the same order. All right, I show the data that already Rolf have shown for the JSI. So these are the new data. Of course, the error bar here, these are absolute cross sections, so you have to consider the error bar. It's 30% right now. I don't know whether there are improvements, but I'm sure that something is in the works where they will actually publish those data. So they added these data. These are projections of hole B, including the fact if they have a pentaquark. And I don't remember what was the coupling that they used, because this looks quite large, but anyway. So these are the simulation. Hole B is taking data right now, so the hope is at some point they start to look at these data and show something. And then last but not least, we talked about Solich, and Bing mentioned it yesterday. I won't go over all this stuff, but the key here is the fact that this detector can take high luminosity. With that, this is what we can do with Solich. You see that the sensitivity will go below actually 10 to the -3. This is in nanobarn. So this is the total cross section. Blue is photoproduction. Red is electroproduction. And depending on what you want to do, but we can in fact detect all particles when we want to calibrate, because you want an absolute cross section and you want to control actually the cross section. I would say to a 10% level at this level. People who can say they can do better, it's great, but we need to be conservative. What you see here is each of these points, of course, is a t-distribution. And I'm showing the t-distribution here. Of course, the statistics is going down, so your t-distributions will not look as good. And the more closer you get to threshold, the higher is the t-min. So maybe this is kind of cheating to show you how far you are from t-min, but you are already at 1 Jeb at threshold from t-min, which means that if you want to know the differential cross-section at t equals 0, you need to extrapolate to t equals 0, which was what was used. Here is a simulation in Solid for 50 days. Say, oh, what can we do with the asymmetry? So you see, this is the invariant mass of the lepton pair plotted against this asymmetry left-right, which we were talking, plotted against the invariant mass of the lepton pair. The J psi is somewhere here. So you see here, of course, you are dominated by the J psi. You don't see there's no asymmetry. But please understand, these numbers are not as large. These are the different T's that I was mentioning, same that were shown in the theoretical curve. But this is folded over the full detector, all the different Q's that are obtained. So it's diluted, but you can actually make a difference between whether it's 0 or non-zero. Okay, so that's the first order. That's, I think, something quite nice. So the focus is on the sideways of the J psi peak. Now, quarkonium at an EIC. The point here I want to make is that the natural quarkonium that you want to use for the threshold region, given the energies and the W's that we want to deal with, the epsilon would be the perfect thing. It's complementary, it is very important. The results better look similar, otherwise we need to understand. Remember, we are using VDM to go from one to the other, at least scattering amplitude. So this would be an important piece. Now, what I'm showing here is epsilon production, and I'm showing the y because really the y is the right variable versus w, so we can measure a large region, and we can also go to the sensitivity of 10 to the minus 3, although this is not fair because the J-psi cross-section is already 10 times more, so you are not here as sensitive just because you need luminosity. What do I show here? If I take a two-gluon model and just change the masses, so the models of Stan Brodsky and company, and I just change the masses, I get a curve that I normalize to the Hera data, roughly. This is, it's one model. And then I see what I can get. So this is the total cross-section in quasi-real photons. So your Q-square is actually quite small. And as a function of W, and this is where we want to go. A t-distribution, just to make it look really, bad, this is what you will be when you are sitting down here, almost at threshold. It's hard because we are assuming here 100 inverse femtobond, so that's 116 days at 10 to the 34. I mean, you look at the number that Rick was showing yesterday, and you could see that, it's a quite nice job that this is doing. I have to just comment on what I said yesterday. In fact, here, the square root of S is 62. So what we did is we played, and we realized that you can be right sitting at where the luminosity is comfortable, so no issues about low S. And then it's the W scan. So what you see here is actually a 10 GeV and 100 GeV. And then the W is scanning. If you try to do the same with the J-psi, it gets much harder. In other words, we looked at different things to compete, let's say, with JLab, and it's hard. Yes.
So maybe you mentioned this already, but
yes.
So you see this striking change in the slope. I don't know if your Stochastic model gets it, or if there's any other side that's
I wouldn't take this model seriously, so I'll show you the next slide what we did. Then we said, we are working on something now with Mark and so on the Upsilon, because we said, if we want to do an analysis like we did on the J-psi, this was what I was showing you before, maybe too optimistic, but even here with the same, the statistics is actually not bad at all. Okay, so this model is actually a parameterization that uses the same type of functional shape that they used for the J-psi, but not like this two-gluon thing, when they use dispersion relations and they try to fit the cross-section, the total cross-section, the differential cross-section, and the open channel cross-section. So the only thing I can tell you at this stage is that I'm not trying to convince you that I will distinguish between this and that and so on. I'm really more interested in having a lot of statistics of how this goes down to 0 or at what speed it's going down to 0. So this part, by the way, when you look at it, you could say that you can tweak, change things so that you can do the imaging for the Upsilon with the Upsilon. And that's why I keep saying, look, guys, don't forget, the Upsilon is really actually an important channel to take seriously, because even at Hera, we don't have much data there.
But just a main question, this two-gluon exchange model, what is causing this change in behavior?
So that's a good question. To be honest, the only thing I can tell you is that I can show the parameterization. I'm actually not sure. You are forced to, of course, stop at that level, but I know that in the previous slide that I showed, when they put 3-gluon exchange, then it stayed a little longer and then came down a little farther away. But then you have to come down much faster, because otherwise you kind of kill the boundary condition.
So the 3-gluon exchange model is really problematic, is what stand there, because they just choose some quadron-like form factor, which is just a sweet parameterization of the quadron.
Yes.
So it's, I think it's really problematic.
Honestly, from the perspective of physics, I'm not trying to. at no point, at least personally, I haven't been trying to say, oh, this model versus that model. Because even the two gluons, I don't know what it means, to be honest. It should be, you know, it should be a blob, and I don't know at what region you can open the blob and see two gluons, let's say, which is what is used with hard gluons at large energies. So I'm with you. Any suggestion? I'm not pushing any specific model here. And I should be done. Conclusions. Sorry. Oops. Heavy quarkonia is an important tool for probing the gluonic fields in the nucleon in general. At large W, it allows, of course, the gluonic GPDs and a threshold it might shed light on the trace anomaly, thus the proton mass. One thing I didn't emphasize, and my colleague at Temple, Marta Constantinou, has actually started to look into the calculations, at least of the matrix element of the contribution of the masses of the J psi and the upsilon, and maybe we can use the relation that Dima was showing to say something about this field. But I think that there is some decent progress. You might notice when you do the lattice, of course, if you go into G's decomposition, you have terms that you can calculate independently as moments. You know, people are doing them with OPE, right? So that the part coming from deep inelastic, where you say something about the kinetic and potential energy of the quarks and kinetic potential energy of the gluons. I think that was one reason why maybe he went that path. Is he was looking at things that you have measured or determined. And at that time, the trace anomaly, he just subtracted and said, this is what it is. JLab and the EIC are poised to contribute significantly to these topics, and that's what I believe. Thank you. I should just now acknowledge. Thank you.
For lattice calculation, direct calculate anomaly is difficult, but they can calculate the charm, heavy part contribution. They can this give some information on the anomaly?
Yeah, so this is what I was showing you before. So if I go in the beginning, and I welcome comments about this, but in the slide where I was showing Dima Karzeyev way of eating the, here. So you can see that these terms, I should have written it differently, but this is the heavy quark contribution, is written, this is documented somewhere in a paper by Schiffman, Weinstein, and Zachar in 78. So in some sense, what the lattice people who have done the charm should try also the beauty in the top and see how hard it is, and then check this type of relation, because through this relation, you see that this is the contribution. Because this came, when it's written here, it's with a tilde. You see, I have no tilde there. So the heavy quarks decouple according to, you know, Dima's talk, and you are left with the light quark. But this is important. So if you get the calculation directly of that matrix, I'm sure that it will help to see the connection. At least, by the way, on the J side, we looked at the numbers. It's not too far to get this contribution.
Yeah, so I have a few set of comments and questions. If you go to your conclusion slide, it might help me make those in some coherence. The measurements that we are now pursuing are J psi as solid, and their importance in the view of you promoted is that we should also make them at epsilon to make a generalized picture. I think that's a very important one. I think there's no question. That's far away from the threshold production. I think there's no question that we should try to do that with the EIC, and it will help. There's no question. The only concern I have is that, so if I understand right, the interpretation of this threshold production, making it the connection to the mass through the anomaly, has certain questions that you raised, right? I'm worrying that this might be a weak point of the argument, to make it at the same level as spin. I understand the effort to connect it, but to confidently say that this is also the measurement of mass at the same level as spin, I'm very worried now. If this is what we are now saying that AIC will do, not should do, will do. Should we not be worried about this? I mean, if the definitions and like interpretations of what that measurement will do to trace anomaly has some questions, and then moving further, I think this I mentioned to you, to you and as well in my last presentation, or somebody asked a question to say that the last physics law that you have shown as 7.1 figure. In your report, National Academy report, there's a figure in which you have luminosity versus center of mass, and then we show the physics blocks of various things that the AIC can do. The last one at the highest luminosity, you say it is. We always used to call it GPDs and TMP. That's the 10 to the 34 luminosity. In your conclusions, in the final part of your National Academy report, you replace that by saying this is mass. I think nobody is going to argue that that's the interactions of quarks and gluons, the energy associated with it, is clearly the mass. So inherently, those are connected. But to say that we're determining that as separate quantities, as shown in this mass decomposition, maybe I'm making a big deal out of this. But
you lost me a little bit just because you switched to. Now I have to think on behalf of everybody in the National Academy.
No, I think it's.
But
so let's take that out. Yeah, I interpret.
We can discuss, but my message is really simple. From what I have been seeing, let's go back just again the comments I made. Jakob Wagner showed at the first meeting in Berkeley. Very nice. Calculations and so on. And you could see that, remember, white paper, we have DBCS, that's an important part of the program, even to reach gluons also. And we made the choice to put the profiles with the JSI, and I think that was not a bad idea. But if you start to now we are moving on, right? So now we are the next phase where we want to actually start to look at things as if we were going to measure and analyze the data and give an answer to the world. And I'm just saying scientifically, my preference would be that as we go forward, if this machine is there, I'm not trying to change the parameters of the machine. I'm showing you what would be scientifically, from my perspective, important, is that we do measurements that without a doubt will confirm our interpretation, whether it's profiles of gluon density that we will claim, or whether it's the mechanism, whether I can use VDM to go from the photon, nucleon, JSI nucleon scattering amplitude to a JSI. We don't have any free JSI beams to go to the other amplitude directly. I think these are real questions. This is now the nitty-gritty at the scientific level. Experimentally, I think it's important to measure them. Lattice, we haven't discussed much, and I'm sorry, I couldn't be here. I heard those discussions also about, photon mass, lattice, and so on. These are all coming together to actually help us really in the interpretation. I cannot imagine this machine with measurements without the theorists actually arguing the case for an interpretation that is clean. Now, in terms of what the perception is going to be outside, right now, if we get the machine, we should get to work. That's all.
That I think we
So there's another question.
Yeah, lesser questions and maybe the thought that we should think of because of the points that were raised, that some of the theoretical interpretation and next to leading effects and so on, as you pointed out. I really think we should maybe use ultraperipheral collisions to get a start on this measurement. There's very nice measurements from on JPSI. Epsilon, I don't think I have yet seen, but I think that actually there is a very interesting community, and maybe we should actually collaborate with them to get some early data before CEIC to maybe help the theory development and then actually get a better understanding whether that is the way for an EIC to make this measurement.
I agree with you. I agree with you.
So I think we should maybe really leverage that a bit more.
Yes.
So going back to what Ray was saying, I think it's at this stage probably important to actually define some program of measurement that elucidates this particular problem. We don't have to say we do these things and we solve the problem, but we have to at least articulate some set of measurements and some frameworks in which the thing can be interpreted to go towards understanding how the mass comes about. Right? So I think we do need this kind of articulate program.
Then I say that this should be in, because that question I don't see. So sorry, I have to be careful. So when Cedric was making his talk, it was clear a while ago, even in the mass workshop, that that C-bar term and all these form factors that usually we kind of put on the side because we weren't necessarily that. We need to look at this, and I think this type of discussions are very important, and also design measurements. How long does it take to discuss that specifically through that path? I don't know. On the other hand, to ignore, because this comes almost together. And what I mean by that is that if you design a measurement, even for the direct JSI or let's say epsilon measurement, they are going to come at the same time. So it's not like I'm saying you should stop and go under. But I think that if you take the comments and the reactions of the National Academy Committee, not the proponent, I'm talking about people watching, this group doing something. I think the mass, addressing the mass, not only theoretically, we should attack it from different things, but not having it in the measurement, I think, is a mistake. That's my personal opinion.
I think it will happen naturally. There is no question in my mind. Your second, third bullet already says that. Right? We are going to make measurement of GPDs. There is no question about it. That is a program. It's the question.
But it's a different.
And I think is the emerging fact is that now the theory and the experimentals now focus on this part. That how can we then interpret that in terms of components of the mass that eventually will build up. I think this is what we are now. I think that's what we should focus on. So what exactly needs to be done?
Yes, yes.
And I'm not against that.
Yeah, so I'll tell you what needs to be done. Right now, I'm not even discussing the part that's not as sure, which is whether you like this decomposition or that decomposition. My understanding is that the two pieces decomposition, the pi and sigma term, which people have measured by other means, and Lattice has focused and calculated it. I think that's ongoing, and that one, there are all the measurements. I mean, Rolf was talking about, accessing the strangeness and so on. So this is a package that's as important, right? I'm saying the other piece. If there are 5 different ideas of measurements, I think that they should come out and we should actually just discuss it, because it will be important to have those two pieces measured, calculated with ab initio stuff, and go with that idea, make it stronger. Look, I had 2 workshops, so trying to follow up, and the only thing I can say is that to let it go as if it will happen by itself and not address it head on, I think it's not a good idea. So that first decomposition is the one that at least, and the theory should correct me right here, that was the least controversial. I had people, there were people, Al Mueller was sitting there, and There were all kinds of, respectable scientists and so on. And my feeling was that that was not where the debate was. The debate was, how do you go, let's say, further in the interpretation and the composition? That's fine. But in terms of the scaling variance and having these two terms, modulo maybe some subtleties that I was hearing in the questions going on, I think we need to look at that and at least say we have a way to measure this piece and we have a way to that's all I'm saying.
I don't want to interrupt. No, sorry, it's just out of my ignorance. So you take the vectorism dominance for granted, but it doesn't work for JPSI in general?
I don't know. So
that's the kind of concern.
No.
This is also not for the EIC just, right? This is even for our JPSI.
That's right.
This is the concern.
So my point is that
I think what you are really measuring is the GPD and the form factor.
Correct.
Yes.
And so from that point of view, there is nothing uncertain about it. We know what we are measuring, what could be interpreted, but you then, because of the vector dominance, uncertainty.
I'm not using vector one.
No, I know you're not, but
well,
Maybe at some level, there are good questions for the origin of mass. It is true, it's undoubtedly true. And look, we have all this question about it, we're making progress. It's undoubtedly that people will throw darts because in the minds of people make too much that there is arguments here, how you can relate this to the phase normally, is it everything, how you measure it, two balloon exchange, three balloon exchange. I think we should just write down what we believe are measurements which can guide us towards the understanding of proton mass. And call that in the right way. And there are certain measurements I think we can do. And I think it's going to be a combination of our theory colleagues about letters and measurements which help us guide our understanding. I mean, that's how we should phrase it.
that's
You're going to get those questions.
But then I think that, we should clearly say what can be measured and what are the questions associated with it. Right? Identify that, those two things.
Yeah, but I think it is a mistake if you wait for the measurements only until an EIC comes. You have to
Absolutely.
take other probes into account.
Yeah.
Whether it is now the program at JLab or what can be done at the LHC, because it might be that some other machine can provide you a missing puzzle which you cannot measure at the EIC. You have to take that as an overall program.
Yeah,
Makes sense. Let us thank Senator Navarro. Come back at 2:30.
So it's not
Why can't